And all the announcements will be up on Canvas. Okay. And then, of course, the lab final is optional. And as and when you turn in your assignments, they'll be grading it. My grades, our final grades are not due until like the middle of next week or so. So they're giving us extra time because some of the assignments, you know, are coming in slow and things like that. Okay. So the TAs are also taking their finals this week. So as and when you finish it, they'll be grading it. And after you look at it, you can let us know if you consider doing the optional final or not, okay? For the lab. All right, nuclear chemistry. This is a fun chapter. Unfortunately, we are doing just a bit of it. You can read on your own, it's pretty interesting. Let's see what I did with my so first we're going to talk about natural deactivity, radioactivity. Now, the elements that are produced or they're synthesized, the last several elements, they are all synthetic, which means they are the PowerPoint is already on Canvas, the one that is not filled out. Okay, I'm answering Daryl's question. And I'm not sure if I'll get to school to post the one that I'm doing right now. Okay, but this without my writing is on Canvas. So many of the last several elements are man-made, synthetic, all right, and they are all radioactive, okay, and most of them, and and they don't last very long, okay, some of them are very unstable. Nuclear reactions, how do they differ from chemical reactions? Chemical reactions, if you know, even if it is oxidation of copper, only the electrons change. There's transfer of electrons. If you take any chemical equation, there's transfer of electrons. The protons and neutrons in the nucleus, they do not get affected. But when you have a nuclear reaction, it alters the number of protons and sometimes neutrons in the nucleus. So this is the only type of reaction where your nucleus is affected, okay, or touched. When you do any kind of chemical reactions, which we've seen so far, and you'll be seeing a lot more in organic chemistry, but they all involve exchange of electrons. They are electron transfers. And with the nuclear reaction, you see, copper is still copper here. But when it comes to nuclear reaction, one element can change to another, and that's called as nuclear transmutation. Now we can talk about nuclear fusion, nuclear fission, nuclear energy used for power production, electric power, and so on. Well, these are the two main differences. There are other differences. Chemical reactions involve electrons. Example, making and breaking of bonds, right? Only electrons. And that too, what electrons? There are several electrons in an atom, What electrons are involved in chemical reactions? Anybody? What type of electrons are involved?
The ones from the outer shell.
The ones in the outer shell, that's right. And they are called valence electrons, okay? So you see how many chemical reactions there are. Anything. How does a virus affect your body? That's a chemical reaction. It's in biochemical systems, so we say biochemical reaction. But it's all chemical reactions. And they involve mostly the valence electrons. Nuclear, it touches the inner core of the atom. Now, in a chemical reaction, if I have two isotopes of oxygen or two isotopes of carbon, you're familiar with these. These two, chemically, they behave the same, okay? But when it comes to nuclear reactions, they behave differently because what are isotopes? Can anybody define an isotope?
Different electrons, but same protons.
Different electrons?
But same protons.
I don't know why, is it my volume that's low or are you talking softly? Can you speak out, Kevin?
Yeah,
I don't know if it's Kevin.
Yes, it's me.
Okay. What is an isotope?
I said there are different electrons, but then they have the same amount of neutrons and protons.
Okay, should we write that in another textbook? I'm just teasing you. Isotope, you're thinking about, I know what you're thinking about. You're thinking about the isoelectronic species. I think. Not even that, I think.
Oh, so it's different numbers of neutrons then?
Yes.
Oh, there you go.
Different number of neutrons. Everything else the same, okay? Those are isotopes. So here, more changes. That's because it involves protons and neutrons. There it is. They have the same atomic number, nuclear charge. This refers to the number of protons. This refers to the number of protons, but different mass number. So isotope, this is one isotope, okay? You can say cobalt-60. When you say cobalt-60, it's automatically understood that it has an atomic number of 27. So isotope refers to the entire atom, including electrons. But then when it comes to radiochemistry, we usually don't talk about isotopes, although we could. We talk about nuclides. We are looking at what's happening in the nucleus. Are the protons, what are the protons doing? What changes are the neutrons undergoing? Okay. So that's a nuclide. Radioactive decay. Okay. So some of the radioactive reactions, they are spontaneous. What does spontaneous mean? What is delta G for this reaction?
It's going to be negative.
Negative. Okay, that's right. Delta G for this radioactive process is negative. And why is it spontaneous? Why is it spontaneous? Now, if I were to draw an energy diagram.
Why is it opening like this?
Okay, somebody's audio. This is energy going up, right? So these naturally occurring isotopes are up here in energy, high. All right. And then they don't like having the high energy, so they keep undergoing changes. Okay. Remember, there's an activation energy and all that process, but it's usually a small hill. And they don't come down in one step. We'll be looking at a diagram a few slides later, okay? So the radioactive decay for some of the naturally occurring isotopes is spontaneous. And that's because they have high energy, which means they are very unstable right here. Nobody likes an unstable situation, right? We all like to be in a state of emotional stability, right? Physically stable. So that's the natural process. So this is called as radioactive decay, right? Now, what are some of these radioactive particles? Now, we've looked at some when we talked about how electrons and protons long time ago, when you all were very young, right? Alpha particle. This is a helium nucleus. Okay. Some of these symbols you'd have to know. Okay. That's why the table. This is the mass number. Z is the atomic number. We cannot forget that. It's just given that symbol, okay? You need to remember that because when we balance equations, you have to know it. So this is the mass number 4. Atomic number is 2. This has a charge because it's a helium nucleus. It's usually written like that, although you ignore the +2 when you balance your equations. So the charge is +2, okay? Now, where did we see this? You remember the gold foil experiment? So they send alpha particles. They hit the gold foil, remember? Now, the beta particle, okay, so you say alpha particle, beta particle, is nothing but an electron. But this is a fast-moving electron. Okay, he's on the fast lane. So how do we represent this guy? Electron. Now, this has no mass number, right? And he has no protons either, but the Z here is going to refer to the charge on the electron. See, this is something you have to remember. Okay. I might even give the symbols to you on the test if I'm nice. And because this is beta, sometimes they write it as beta -1, 0. Okay. Same thing. Positron, okay? Positron, electron, positron. So what's the difference? It is like an electron with no, remember, electron is very light, right? It's not as heavy as a proton. So the positron is not a proton, is as light as an electron, but it's positively charged. So it has no mass. The Z here refers to the atomic number or charge. We make this distinction in nuclear chemistry. Like an electron, but positive. Okay. So what all do we have? You've learned about the alpha particle before. You know about electrons. So the new addition is the positron. And I said it's like the electron, but he is positive. So because he's like the beta particle, you can also say beta plus 1 and 0. Gamma. You all know about gamma. What do you know about gamma? Where have you seen gamma before? Gamma rays, where did you see it?
In like the wavelength.
Yes. Electromagnetic radiation. Okay, so you need to relate to what you already know. And this is radiation. Does it have mass? No. Like white light doesn't have mass? No. Charge. Okay. Gamma. And for balancing equations, we need these symbols. To say gamma, 0, 0. High energy photon in the electromagnetic radiation spectrum. This guy has the highest energy. Remember? So we'd see these given off in a radioactive reaction. So you have to know these, okay? And you'll see how it's used to balance equations, okay? We are going to learn baby chemistry today. Now I'm going to elaborate on this a little bit more so it sinks in. Alpha particles. Do you know the symbol now? Okay. So how many, and this is a 2+ charge, which is not shown. Okay, that's why the circle. So how many protons? How many neutrons? Protons is 2, neutrons is 2, electrons is 0. Okay. Take in what we're doing now. Just relax and just learn, okay? All right. Beta particles, what did I say? These are fast-moving electrons. How do you symbolize it? Mostly they say beta -1, 0, or electron -1, 0. Okay, we're reviewing. These are also fast-moving. They are like electrons, but positively charged. With a positive charge. So this is beta 0 plus 1 here, or electron plus 1, 0. Okay. Gamma photons, right, of the electromagnetic radiation with very high energy. Okay. Review of the previous page. Got it? Now you may want to keep one of these handy for when we do the equations. Radioactive particles are not atoms, like helium. It's not an atom, it's an ion here. See that? And in some cases, so here are they sometimes say alpha instead of helium. For the beta, the -1, or the beta +1, 0. These Z values refer to nuclear charge or nuclear charge. Okay, now let's look at specific equations. And if you know how to balance those oxidation half and reduction half in acidic solutions. By the way, for those oxidation half and reduction half, you need to know how to balance those only in acidic solution. Okay, so we won't worry about basic solution. So only acidic. I'm going to write it here. Balancing redox reactions in acidic solutions only, not in basic solutions. Okay. I said I was going to do that, but it's a very slight variation. If you need to learn it, you learn it in analytical chemistry. You won't worry about it here. Okay. Side note there. So how do you balance these equations? So here, remember, you have an unstable isotope. It will disintegrate. So we use such terms here, disintegration. This is the same as decomposition, okay? So it'll give a daughter nuclide. Remember, these refer to the nuclear part. And then a radioactive particle. So let me give you an example. You've heard about uranium, right? 238 is radioactive. Now, when I say uranium, then you need to know its atomic number from the periodic table. I'll give it to you. This is unstable. It's going to give you TH, which is thorium. So you'll use these elements that you've not used before. 234 and 90. Okay, now we're going to start learning how to balance equations right here. So what do? It's math. Okay, so the total mass number here is 238. And what do you have here? 234. And then atomic number on the reactant side is 92. What is it on the product side? One of them is 90. All right. So it's simple math. The mass number difference is 4, right? To balance both sides. What's the atomic number difference? 2. among the radioactive particles, how many do you know? 4 of them. Which one has a mass number of 4 and an atomic number of 2? Wow, that is so hard. See that? So you need to balance both mass and they say nuclear charge. So you need to balance the mass number and the atomic number, okay? All right, so have the other sheet handy with the symbols if you need to. Now, we just saw you made an alpha particle, okay? I'm going to rewrite that here. Thorium, okay, that's thorium 234, and it gave helium nucleus. So this is called an alpha decay. Okay, type of reaction, alpha decay. So what is happening? An alpha particle is ejected. And the difference in mass number is 4 and the difference in atomic number is 2. And so your equation is balanced. Now let's look at beta decay. Again, remember the symbol for beta, -1 electron, right? 0. You don't have to remember all the symbols for each particle. We'll be using some routinely, so remember those. Now here, if you look at it deeply, how is an electron coming out of a nucleus? Okay, electron, this is actually coming out of the nucleus. Ejected from the nucleus. By the way, just like how we learned the electronic structure, you had different shells, and inside the shells, you have the orbitals. So there is an organized pattern of how the protons and neutrons are arranged inside the nucleus as well. Okay, so if you learn nuclear chemistry, and I had a graduate course in nuclear chemistry, and so you've only seen what's inside the outside of the nucleus, inside the atom, but inside the nucleus as well, you have a very structured pattern. So I believe in an intelligent designer. So ejected from the nucleus, how does that happen? A neutron becomes a proton and gives off a beta particle. See that? Okay, so how do you balance an equation? This is how it's produced, but let's look at a specific equation. Carbon 14, remember it's used for finding the age of fossils and things like that. 14 and 7. Can you balance this equation? Is the mass number balanced? How about Z? So here, I'm not going to put, I can also put a positron there, but this is clearly, okay, I say it's clearly, but you'll be given hints about what type of a decay we are expecting, okay? Otherwise, you can give answers that'll work here. So mass number is balanced. Atomic number, I'm going to say Z, okay, because it's not just the number of protons, it's a charge. So you have 6, 7, and -7, -1. So that's how you can show work. Got that? All right. So you have alpha decay, beta decay. I think there's a problem here. Can you try this? Thallium, okay. Don't have to know their names, but you should be able to pick these out correctly from the periodic table. This is 81. Sorry. I think there's a mistake here. Okay, thallium, says thorium. Okay. Everything is the same, but the symbol is different. Sorry, there's a typo in the notes and it must be lead because thorium is not 82, okay? Sorry about that. If you're writing with a pencil, please erase it. This is lead because lead's atomic number is 82. Thorium's atomic number we just saw was 90, okay? So thallium, 210, 81 going to this. What is the other product?
It's going to be the beta positive.
Beta positive?
Negative. Sorry, negative.
Beta decay, okay? So it will be, these usually are given off, okay? Particles are given off. So I'll tell you a case where you will put a reactant, okay? So particles are given off. Theoretically, we can do other things to balance the equation, but keep in mind that beta decay, which means beta is given off, positron emission or positron decay. So positrons are also given off. Okay? So you have a beta particle produced. Gamma, most radioactive decay, they release gamma particles. Some give only the gamma radiation. So that it looks as if there is no change. And you don't even have to report it. But what happens is, this is high energy. And when it gives off gamma particles, this becomes low energy. Okay. So this is called as the daughter isotope. Everything looks the same except, you know, they are lacking energy. So many radioactive reactions, although they give off alpha particles and beta particles, positron emission, they may also give off gamma rays. And because there's no change in mass, it's not accounted for. Okay. Positron emission. Okay. So beta emission, positron emission. So the beta particle and the positron, they are written as products. So there's no confusion. And then we have, this is the fifth kind. It's called electron capture, written as a reactant. Okay. So keep that in mind. So when you have positron particles or beta particles, they are written on the product side. I don't think I have a specific example here. This is a positively charged electron. Now, electron capture. Okay, what is this? How does this happen? So you have, let's say, 5 neutrons and 4 protons, okay, inside a nucleus. So during a nuclear reaction, this is drawn into the nucleus. The electron that's closest to the nucleus, okay? It's like strange things that we've not read about before. And then what happens? It sucks it in, and then the electron and the proton, they become, I'm sorry, my numbers are off here. Proton is converted to a neutron. So you have 6 neutrons and 3 protons. You see that? Now this becomes a different element. 4 protons, that's beryllium. Okay, for example, this is beryllium, 4 protons. With this sucking in of the electron, right? This becomes lithium, for example. I don't know if this happens, but just to show you. So this is electron written as a reactant. I don't have an example here. We look at it in the next slide. Got that? Okay, so beta particles, positron particles, they are written as products. And the electron capture, when it says electron capture or K capture, then the electrons are written as reactants. Got that? Okay, let's try what's on the next slide. Now you have to fill these. Let's try B first. B. What's the answer? I want everybody to try. Do a mass balance, balance the mass number, balance the Z value, and what do you get? Answer for B. Are you doing them all? All right, anybody? What's the answer for B?
I said helium.
What did you say?
Helium.
Helium?
Yes.
Okay. So the question mark is helium for 2. Jessica, what's the answer for C?
Hold on, I'm doing it right now.
You're doing it now. There are 2 question marks. Okay. But here they've given you the mass number and the C.
I
Okay.
mean, the first question mark is it's nitrogen.
This one here is nitrogen.
Yeah.
Okay. So 14(6). Now, how do you know it's nitrogen? You use your periodic table and the atomic number is 7. So all of you must have a periodic table to do this. And there's no change in the mass number. So this is 0.
And then -1, so then the beta.
Beta, right, very good. Beta particle. Francis, D. Are you in the room? He's gone out. Tom, you got an answer for D? Take your time. Well, there are 3 question marks. Let's start with the first one. Now,
I'm
many
sorry,
of you
my
may not have.
my Wi-Fi is not very stable right now.
What is it?
Okay, so D, you have 18 and 8.
Mhm. Yeah, okay, 18 and what is this? 9 and 18? What's the element with atomic number 9?
Chlorine.
Fluorine, right? Yes. And then it gives something with 8. You see, these cannot be different. It's only what is in the periodic table. So before fluorine, you have oxygen. Now, what's this difference here? 9 and 8, so this should be a +1. What is the one particle that you know has Z as +1?
Hydrogen.
Hydrogen?
Positron.
Beta.
Radioactive particle.
Beta positive.
Yes. So you're not going to use an element here. It has to be a radioactive particle, the ones that you've learned. So this is beta. And beta is always 0. Do you all understand? So it's an actual element, and because it says on top, complete the following radioactive decay. And you cannot put hydrogen because hydrogen is 1 and 1. I see you would have then adjusted the mass number for oxygen. But because they say radioactive decay, radioactive decay, this is beta with a +1, 0. Now you can balance this. This is oxygen 18. Okay. The question is, can you use this? Okay, hydrogen 1 and 1. But this is not a radioactive particle. Okay, so you must use one of the particles that you have learned about. And if it says decay, then it has to be one of the 4 that we have talked about: helium, beta, positron, and the other is radiation. Okay. And if it is a product, then it has to be either helium, beta, or positron. Oh, we didn't do the first one, did we? Now here it says decay, but then the question mark is referring to a reactant. You see that? So if it specifically says a reactant, then the only reactant that you know of is the electron capture. So how do you represent electron capture? C6H11. Let's fill in the blanks first. What's the difference? It says the reactant, it's a reactant. So this must be -1, 0. Okay. And our tendency would be to write beta here, right? But since they say electron capture, they're trying to differentiate this from the beta particle that's emitted at the end of the reaction. And they put the E sign, okay? It's same as a beta particle.
Dr. Mary, so every time we're talking about reactants, are we gonna use the electron rather than the beta?
Yeah, if it's an electron capture, they put an E instead of beta. Okay. Now, give me a second. I want to give you a couple other reactions. Do a new share. Okay, do you see this here? Question number 2. Do you see that or not?
Yes.
Well, let me write it down and then I'll, it looks like some of you could use more practice. Let me write it down and then I'll. The symbols are different here, but don't worry about it. We'll only use the symbols that we are talking about. Try 2A while I copy some of these. Now you know why I give you homework? It's easy to just teach without doing practice problems. Okay, I'm going to go back to the document camera. Okay. Try this one first. That's bismuth. And let me give you the atomic numbers. So you'll need a periodic table. You may want to grab one. Lead is 82. Bismuth is 83. Tell me what that answer is. I'm going to start calling people randomly. So gear up. Bismuth, Bi.
Dr. Mary,
Yes.
would it be plus after the bismuth? It would be 0 plus 1. The beta symbol.
This is 83, right?
Yes, ma'am. It increased from 82 to 83, so it's a plus 1.
Yeah, but what will you put here to balance it?
-1.
See, if you put a +1 here, 1 and 83 becomes 84.
Oh, okay. Yes, ma'am.
And what is that particle that is -1 and 0?
Beta.
Yeah.
Beta.
base particle.
You have to start memorizing these as we do it. Okay, so then this is beta emission. All right, try the next one. I'm going to turn the wheel. Emma Henry will answer. So this is 7, okay? Do the calculation. Just like you learned how to balance equations. This is 13. You don't know what this is? plus 0. And then Z, you have 7. You don't know what this is. And this is 1. So what is that unknown? See, you have the radioactive particle here. So this must be an element from the periodic table. Emma, do you have an answer? Emma's not listening. Chat. No, I can't hear you, Emma. It's okay. Do you have your audio off? That's all right. Just answer there if you know it. If not, it's okay. Maddie's probably reclining. Carbon, yeah. Emma, I can read what you're writing. So she says it's carbon. Thank you, Emma. She says it's carbon, and this has to be 6, right? Because 6 plus 1 is 7. You understand, Ralph? And then this is 13, and this is 0. So this must be 13. So do your math on the side, okay? Don't be in a hurry to get to the final answer. And this is 6 and 13. Very good. All right. The one below, please. Will you have an answer? It will be difficult if you do not have your periodic table. 210. This is 4 plus. Now you know what it should be, right? 206. Z, 86. This is 2. So this should be 84. Okay. What is on the periodic table that is 84? Right? Did y'all get 206 and 84?
Yes.
All right. So it's polonium, 206 and
Yes.
all right, great. We're just going to do these two. I'm going to give you a minute quickly. Find the periodic table on your phone. Practice, practice, practice. And this I put electron, but you have to give the proper symbol, which is E -1, 0. And let me give you thorium. Is that 92? $90. $92 is uranium. Argon, 18. Okay. Then we'll go on to kinetics. First one, Adrian, do you have an answer?
Yes, I do have an answer for the first one. I got RA. I don't know how to pronounce it.
Radium, yeah. RA, very good. And then, is that 88 here? Is it 88, Adrian?
Yes.
Okay. And then what is it on top?
It's going to be 226.
226. Yep. Did everybody get that? You have questions?
Yes, I got that.
Okay, good. All right, try the last one. We're done with that. There's one more. PB is 82. Sulfur is 16. I'm going to tell you here, this is another element. Unless I didn't write something correctly. So this is 37 and 18. 37 and 0 is 37. 18 minus 1. Okay, do the math. Everything on this side should equal everything on that side. So this is 17. What is the element that is 17? It's the L.
Fluorine.
What's the other element? That's what it should be on this side. Wrote it down incorrectly, but still do the math.
Oh, Dr. Mary, you would subtract one instead of adding one. I thought if it was a negative, you would add it.
No, what is 18 minus 1?
Oh, okay, so we're
17.
doing basic. Okay, so I was doing the opposite. So I was doing 18 plus 1. Okay, thank you.
Yeah, it's just do the basic math, okay? Yeah. Just a little tricky with the negative signs. What's the other element? Elma, what did you get? I think I made a mistake there. It shouldn't be sulfur. Just a second. Lead. And lead cannot have 30. Oh, I know what it is. Sorry. It must have been like, I'm learning new stuff now and she's confusing me. You know, the mistake is, it's phosphorus, because PB cannot have 30. It's much higher. So phosphorus 15. So I wrote it as PB instead of phosphorus. Elma did all the research in the world.
So it's going to be the beta particle. So 0. So yeah, 0 and then -1 with the B symbol.
0 and -1. Okay. So yeah, I knew something was wrong. I thought it was wrong here, but that's the mistake. Everybody clear in spite of my mistake?
Yes.
All right. Okay, I think we've done enough practice. So let's get on to reviewing first order kinetics. Now, there are several applications of nuclear reactivity. One is a smoke detector, and the other is a Geiger counter. Okay, counter. So this is used to detect the amount of radioactivity in the area. So it works similar to how, you know, the smoke detector works. It's a little bit, you know, there are differences, but I'm going to just show you an example here. Some of these, so I'm not sure if yours has this. I don't even know what mine has. But some of the smoke detectors, they carry this radioactive isotope, okay, americium-241. And normally what it does is it, you know, releases a little bit of the alpha particles. It's all controlled. And so the air that is in the room is ionized because this is positively charged, okay? This is 2+ charge, so it ionizes the air in the room, and the positive ions go to the negative electrode, you see that? We've learned electrochem, and the negative ions go to the positive terminal, okay? And then this is under normal circumstances, this is just air. Now what happens when there's smoke in the house? This blocks this ionization. So there's no free flow of current. And that's when the alarm gets triggered. You see that? Now, when you use a Geiger counter, the radioactivity in the area or in the vicinity of where the counter is held, this will start, it'll start counting. It'll be a different setup. I'll show you one that's in your textbook, a picture. But the amount of radioactivity for every particle that comes in, it'll take that into account. Okay? So that's what is a Geiger counter. And if you work in a radioactive lab or a nuclear power plant, then you're supposed to wear that. And then you're allowed so many doses per day, okay? And if it goes above the limit, then you have to move away from that area. So radioactive series, now remember we talked about uranium-238. This is unstable. Okay, that's what is also used in nuclear fission. And then remember, I had the little activation energy and it drops down to produce the most stable isotope. Look at all the changes it undergoes. It loses an alpha particle, and this is where I think it becomes thorium, and then beta decay, and then it loses another alpha particle. Every time it loses an alpha particle, it becomes a different element. See that? So it doesn't go from here all the way to there. These are the steps that take place. Look at all these changes. And then ultimately, it's like, okay, I've reached lead. And that's where it stops, okay? So anything above lead 82 in the periodic table, it is unstable. So this is called a radioactive decay series, and you can show something like this for every radioactive isotope. Got that? And this is a chart. It tells you these are where the isotopes are, okay, that are stable. If you have isotopes with too many neutrons in that blue region, they're unstable. If they have too many protons, then they are unstable. So all of the elements that lie in this region, it's called the belt of stability, then they are stable isotopes. Okay, so just a qualitative explanation for you. Okay, first order rate law. How many of you remember this? What is a first order reaction? We all started reviewing chapter 14. Waiting for something to happen before you review. Can anybody give me the rate law? Rate equals what?
The concentration of A. Oh, my bad. Multiplied by the concentration of B.
First order.
Oh,
A giving products. If it's first order, can you have two reactants?
oh, that's right. It has to equal 1. That's my bad.
Yeah, unless B is raised to the power 0.
Right.
Okay, yeah, that's possible too. All right, good. So rate law. So our nuclear reactions, they are almost all first order because it's one isotope that decays. So it is one isotope which is involved in the reaction. So A is raised to the power 1. So radioactive reactions they follow first order kinetics. You need to learn about second order and 0 order, but in this chapter, because we are studying nuclear decay rates, we learn only about or review the first order reaction. Now, we say rate in the rate law. If you do sampling, you'll see that they are, I'm just going to say isotope. Okay, that's a rate law. Now here, instead of saying rate, which is molar per second, this is number of disintegrations per unit time. Okay, that's why I took away the A from there, because the rate here is sometimes referred to as activity A, but A is our rate. You can use the same equations that we've used before. And the concentration of the isotope, because it's the nuclide, they refer to this as the concentration of the isotope. And it doesn't have to be molar because these are radioactive. So it's not referred to in terms of concentration usually. So N is referred to as the number of atoms of the radioactive isotope present. And this could also be the number of grams, okay, of the isotope, or number of atoms of the isotope. So you have to keep that in mind. That's the same as concentration numerically. And K, the rate constant, is also called, because it's referring to decomposition, nuclear decay, it's the decay constant. And of course, each radioactive isotope will have a particular rate constant. Got that? So here, the equation can be written as this: activity, this is the same as rate, K, to the concentration of the isotope. Okay, please keep that in mind. I'm going to use our old equation, so it's consistent and it's, you know, easy to keep track. Got that? So in sampling, like the few questions that I have, if they use this equation, remember, refer to this slide, and it is the same as this. Okay. Now remember half-life. What is half-life? How much time? I'm going to go over it. I don't know if you've reviewed yet. It's the time it takes for a sample to get to half its original value. Okay. So remember, if you have 1 molar of a solution, to bring it down to 0.50 molar, if it takes 30 minutes, then this is called half-life, or T half. Okay. What's the equation? T half is 0.693 divided by K. Okay. So this these equations will be given to you. So for a first order reaction, T half only depends on the rate constant. It does not depend on how much of the isotope you have, or the initial concentration of the reactant. Does not depend on how much of the isotope you have. It only depends on the rate constant or the decay constant. Got it? So we reviewed the rate law, and then for the first order reaction, and then T half for the first order reaction. You would have seen something like this in chapter 14. Now here, instead of concentration, remember I said they do not use concentration. It's not diluted in water or anything. So it's just mass or number of atoms. So here they have mass. They have, I think, started with 1 gram. Well, they started with 0.8 gram of the substance. Okay. How much time does it take? They don't tell you exactly how. Oh, it does say 1 minute. Okay. So 1 minute to come down to half the concentration. You see that here? It takes 1 minute. Radioactive reactions are fast. Okay. And then from 0.4 to 0.2. It takes another minute. And then 0.2 to 0.1, it takes another minute. Why is it the same? Because T half does not depend on the mass or concentration for regular reactions of the reactant. For second order, it's different, and 0 order, it's different. But for first order, it does not depend. Okay, this is only for first order. Review carefully. Okay. So this is first half-life, okay? Second half-life, third half-life. So it's gone from 0.8 to 0.1. And then another 1 minute, it'll go from 0.1 to 0.05. So it'll take a long time to die out. That's why when you have these nuclear disasters like in Russia, Chernobyl, and recently, was that in Japan? Okay. So it takes a long time, especially if the half-life for some of the isotopes, they are very long. Not like the medical radioisotopes. Those are short-lived, isotopes. But others, they take years to get to half the concentration. So that's why it takes a long time before that area could be considered as safe. Okay. Okay. So these are some of the half-lives. But how they calculate half-lives, that's under discussion, and some claim that it's not very accurate. But if you look here, this is like 10^9 years. Carbon-14 is 5,700 years. So some of these have very high half-lives. So even if you used, I think for the bombing of Hiroshima and Nagasaki, they used only about 1 kilogram of the material. So, and it produces a chain reaction, and therefore you do not need a whole lot of the source material. These are some of the radioactive isotopes, okay, that is used for medical purposes. Not thorium, I'm sorry. I think I picked wrong examples here. I'm going to just highlight this. I was looking at another table, perhaps. Iodine-131 is used as an medical isotope for thyroid issues. They're now no longer using iodine-131. I think they're using iodine-123 is what I read. Okay. So some of these are not medical isotopes. I know iodine is, but none of the others that are listed here. Okay. So that's an interesting field, radio medicine. All right, let's do some calculations. Need your calculator. Time required for 60 grams of the sample to be reduced to 7.50 grams. Okay, start thinking about the problem. How will you set it up? Now there's another equation, but that equation requires K. Okay. Let's do this. And this is carbon-14. Okay. So carbon-14, 6, from the table, okay, the one that I just showed you, T-half is 5,730 years. Okay. Especially with carbon dating, some claim that the method itself is not too accurate, but they still have this value listed in the table. So we're going to go with that. This is for 1 half-life. So we can do a simple math.
4 times, you have to divide it 4 times.
You're saying 4 times?
Yeah, I think
So
it's
this is, yeah, 1 T-half right? For half the concentration. And then 30 to 15, 5730 years. That's another half-life. And then it's not 4 times, is it? It's just 3 half-lives. Okay, so this is baby map. You can add up all the years because it went from 60 to 750. So the total but you cannot do all the math that way. So with the next problem, I'm going to show you, I think, another. Okay, there's another method to do it. I'm going to show that to you with the next example. Hang on with me. A few more minutes. Okay, still have 20 minutes left. So you have T half is equal to 0.693 divided by K. You also have the integrated rate law. For a first order reaction. This is all for first order. Okay. Do you remember what that is? ln AT minus KT plus ln of A0. Remember? So this is the amount of substance or isotope present at time t. Okay. I'm using the same equation that we had before, so there's no discrepancy. But instead of concentration, I'll just put grams for the radioactive reactions. A0 then is the amount of substance present initially. Okay, or concentration of substance present initially. Is 0. Okay. Now I'm going to use this method, although you can use the method that I showed you before. You have to do this in 2 steps because you have to find K first. So AT is the same as NT, right, for the radioactive isotope. At any time, 10.8 milligrams. Read the problem. Certain isotope, 43.2 milligram is the initial amount. Okay. 43.2 milligrams. Okay. And T is given 59.6 seconds. So the first step is to find K. And then after you find K, you can find T half. So can you do the math? ln of 10.8, you can ignore the ignore the units, minus K, T is 59.6. This is second, so K will be -1, okay? K will always be time -1 because it's first order kinetics. Do the math, you should be able to do math. Tell me what K is. And you must show your work using the math editor. If you give me a final answer, and even if that's right, if I don't see any work, I will not give you full credit. You don't have to give me every little detail, but I need to see the setup. Find this, do it systematically, find that, bring it all to one side. And write the numbers correctly. Do you have anybody with a K value?
Dr. Mary, I have 0,
Scientific, please, scientific.
2.33 times 10 to the -2.
Unit,
m-1.
you're solving for the rate constant.
Would it be s-1?
Yeah. Did you all get 2.33 times 10 to the -2? I don't know what the answer is.
Yep.
Yes, okay. So that's K. You've not solved the problem because they want half-life. So from K, you have to use another equation to find, okay, step 2. And this will be in seconds because what's t half?
Thirty seconds.
37?
It'll be 29.8.
Yeah. That's what I have. Okay, so if t half is asked, then this is the numerical way to do it. We'll do one more like this. So you have ln of AT Okay. Now, if you want to write it for nuclear, for this chapter, you write it as ln of NT, because it's not concentration. ln of N. Okay. And this can be number of atoms or mass. Okay, this could be grams or milligrams or kilograms.
So it doesn't matter what if we have it in milligrams or grams.
No, it has to be the same though. NT and N0
Wasn't
must be
something
both in
other
grams
than
or
grams or
both in milligrams.
grams.
All right, can you try this one? Half-life is given, so how will you set it up?
Hey, Dr. Mary.
Yeah,
If it's in something other than grams or milligrams, do we need to change it to grams or milligrams, or can
no,
it be anything as long as it's
as long as they
equal?
are the same, it doesn't matter. Could be pounds, ounces, okay? Can be anything, as long as they are the same. The only thing, it cannot be concentration, that's all. It's not possible. But if somebody were to prepare a solution and ask you to do the calculation, that's fine. What must you do first? Can you find half-life in one step? Half-life is T half divided by equaling 0.693 over K. Do you have K? You do not have K. Please read the problem. Find K. Set up the equation, find K.
Doesn't it tell us the half-life in the equation or in the question?
What does it say?
It says the half-life of the isotope is 73.5.
Oh, half-life is given. Okay. So half-life is given. So use that to find K. Sorry. Yeah, you're right. I didn't read the problem. So find K using this equation.
Dr. Mary, don't we, for the units, don't we use seconds?
No, you change depending on, it can be
okay.
anything depending on what T half is.
Okay, yes, ma'am. Got it.
Yeah, yeah. So here it'll be per hour.
Dr. Mary,
Yeah,
it said 1,114.8 hours.
K value.
No, that's like a final answer.
Oh, calculate the time. What did you have? What do you have?
1,114.8 hours.
No.
Okay, thank you. I just did it differently. Yeah.
Okay. So what is K?
I got 9.43 times 10 to the negative third.
Case. I don't know why I think my volume is low. Can you say it again, Adrian? I think it's
Yeah, I got 9.43 times 10 to the negative 3.
okay. Thank you. Hour minus 1. Okay. All right. Then let's find T for the problem. For this one, you use ln. Okay. So ln of write the correct number in the right spot. Atoms. Okay. Minus K, which is 9.43 times 10 to the negative 3, hour minus 1. Time is what you need to find, okay? Not the half time, but the time for this integration to take place, disintegration to take place. 6.75 times 10 to the 18 atoms. So calculate this, calculate that, and I'm going to wait for a T value. That's same as what I have. Should be in hours.
I got 215 hours.
215, that's what I have too. Are you all getting 215? If not, check your answer. I have one more problem, and that's be the last problem.
Dr. May, how did you get 215 hours?
I didn't get it. What do you have for this?
Are you saying so when I subtract the natural logs of both of them? Yeah, so for that I got negative 2.026.
Negative 2.026.
Yes, ma'am.
Okay. This should equal negative 9.43 times 10 to the negative 3 hour minus 1 times t. Did you divide this by negative 9.43?
Yes.
Maddie, did you get minus 2.026 for this part? Or anybody else?
Yeah, I had that, and then you just divide by negative 9.43 times 10 to the negative 3, and then you should get
You should get it.
215.
Okay. Did you put this in parentheses?
I think that was my mistake because I was getting something that was in the millions. So I worked it out though. I got the
Okay.
same.
Okay. All right, so be careful, and you have to put this within parentheses, especially if there's scientific notation values in the denominator. Okay. Let's do one last one, similar to this. So again, half-life is given. I want you all to set it up. What should you do first? Can you do it in one shot? What should you find first?
You should solve for K first.
Yes, solve for K first, yes. So tell me what K is.
I got 0.03387.
Scientific, please. What
Yeah.
is K?
Just give me a second.
Sure.
So 3.7 times 10 to the negative 2.
3.7. Can you give me another sig fig?
3.872
Oh, 872.
times 10 to the negative 2.
Negative 2. Unit will be?
What'd you say?
Mhm.
Unit?
This is going to be a minute negative 1.
Yes, correct. Good. Give me NT.
1.76 times 10 to the
What do you have?
1.76 times 10 to the 19.
7, 6.
Yes, ma'am, times 10 to the 19.
Yeah. That is correct.
Dr. Mary,
Mm-hmm.
have we received? So what is the answer for this problem? The for part B, how many atoms?
Here,
Uh,
have it on the screen. (1.76 times 10 power 19). Did you all get it?
Yep, I got the same thing.
Okay. How will you convert ln A NT to NT? What's the answer here? Anybody? What's the answer on the side?
Are you talking about the one?
Let me get closer to the computer. I think I have my volume down. What is it?
I said, are you asking about the 1.76 times 10 to the 19th? Are you asking how we got that?
No, I'm asking for ln of NT.
Okay.
If you don't have it, that's okay. Did everybody get it? If you got it, then I'm not going to worry about it. Okay. I think everybody got NT.
Yeah, I'm kind of confused now. Like I don't know which value you're asking for.
Did you get NT is 1.76 times 10 power 19?
Yeah,
Okay.
yeah, that's oh,
Okay.
okay. That's me.
Okay. Yeah, that's all. I was trying to help somebody get there, but if everybody got there, then that's good. Okay. Now I want to show a couple of things and then we'll stop. So here, Are you able to see this section in your interactive textbook on the screen?
Yes, I can see it.
Okay. Okay. So can you all see that? I think everybody can. So this is the section that talks about nuclear fission. So you have a large isotope here that's bombarded by a fast-moving neutron, and that splits this big isotope into two daughter nuclei, and then more neutrons are released. So then these three neutrons go and attack another molecule of uranium, and more of these are produced. So that's how you have a chain reaction that becomes unstoppable. Okay, so this is a little video. See how it starts and it keeps, it's sustained until there's something else to block it from happening. And this is a diagram of a nuclear reactor. So you have your fuel rods, which is uranium, and then there are control rods to control the number of neutrons that are released, and then the high energy that is produced. You see how it is generates power. Okay, electricity. A number of European countries, they use this, you know, to produce their power more so than we do here. And this is a site. I don't know which one it is. Okay. Nuclear fusion, for this you need high temperature. So naturally it happens near the surface of the sun. So smaller nuclei, they combine. This is an example, isotopes of hydrogen, and then more energy is produced. Okay, but you need a high temperature to initiate the reaction. And they're talking about other things. Okay. I saw somewhere, I think it was here, that they use for the probes that they send to Saturn and Pluto, they mostly depend on solar energy for their energy, you know, as an energy source, but they also use nuclear energy, and I think they have nuclear cells or something like that, and that produces the energy they need. I think I saw a picture of that. Okay, bottom line is, since you didn't have science club at the end of the semester, and I'm going to list how many words, probably about 500 words. On this section, 20.5, fission and fusion, I'll open up a discussion board, and then you can get up to 5 extra points. And I'm going to make that due like later in the day on Thursday, like by Thursday midnight. Got that? So write up about, I'll post this on Canvas, write up about fission and fusion, and you'll get up to 5 extra, up to 5. So if you write 2 sentences, then probably not the whole 5. Okay.
Okay,
And
Dr. Mary,
you can
tell-
if you write what?
Would you be able to let us know if we already have 15 extra credit points or not? Because I know we can only have 15 like for the total semester.
Yeah, I'll make this open to everybody.
Okay, thank you.
Okay, yeah. I'll make this available to everybody. And so it's 5 extra points. And this is directly related to lecture, so it might go in a different column. But it'll be due Thursday by midnight. Okay.
Thank you.
So the sapling assignments that are due are already posted. I just posted it at the beginning of class. And then I'll open up a discussion for this as well. Okay. And then we are going to start at 12:30, check in. And then once everybody's checked in, then we'll start the test. Okay. So everybody must be on Zoom with your phone, and then your laptop or iPad, only one other device in the room will be used to take the test, and you'll be allowed a calculator. And your calculator shouldn't have any of the quadratic formulas. I'd like you to solve the quadratic formula. You don't have to show all your work on the test in the math editor, just what you get for A, B, and C. But I'm going to keep it uniform. Nobody will use the calculator for any of the quadratic equation solving. I hope all of you are listening, because last time I said that and still some of you used it on your calculator. And I'll take off points if you do it this time. So hope all of you are listening.
Dr.
I'll
Mary,
post this on Canvas as well. What?
how do you want us to show that then?
I just want you to show me A, B, C values. You can do your work and you can set up the final equation. You can say x squared plus bx plus c is this, and then and give me values for A, B, and C after you hand solve it.
Okay.
I want to keep it uniform. So your calculator, it should just be a scientific calculator basically, but you can use whatever calculator you have. It shouldn't be programmed with any other information. So everything else, you will show me calculations, basic or important calculations that lead from step to step. You do not have any ICE tables. I mean, you will have ICE tables, but I'll show you how to show that on the test. I'll give you instructions specifically. And if there is any upload that needs to take place, I'll let you know at the beginning of the test. But if any upload is to take place, it has to take place right after the test is over with. And that's all I have to say. Okay. Anything else? Your lab score should be out in a few days. And the lecture, I will be converting your sapling only after you're done with everything on sapling. Otherwise, I cannot pull it over. Okay.
How do we know if we've like reached our limit on extra credit? Like, will you let us know, or are we supposed to know ourselves?
It's on Canvas. There's a column that says extra credit.
Okay.
But this extra credit for 20.5 write-up, it's specifically for lecture, not science club. So I'm going to have it available to everybody.
Okay.
So it'll show as a different column. So the column that's already there, I'll say extra credit science club or something. And then I'll say extra credit fission or fusion or nuclear chemistry, something like that. Okay, but because I want you all to learn from this section if you want to. It's, it's extra credit, so it's up to you if you want to do it or not. But it has to be done Thursday midnight. And I doubt I'll have all your grading done that quickly. That'll be a miracle. And like I said, our grades are due sometime next week, after Wednesday next week. So I have a little bit of time to grade and convert all the sapling over to, transfer the sapling over to Canvas. And so that takes time. But as soon as the exam scores are graded, then I'll be posting it on Canvas. All right, so if you have any questions between now and Thursday, email me, and then we can, do it over email, or if we need to set up a Zoom session, we can do that as well. Okay. All right, guys, few more days. We're almost there. So take care, and hope all of you are registering for your classes. Try to do it sometime this week if you can. So you can get that also out of the way. And remember, if you are going to take physics next semester, then you need to be in the Tuesday lab for organic. So keep that in mind, otherwise you may not be able to take physics and organic at the same time. All right. Anybody want to say anything? Okay. So I thank you all for this lovely for the most part, right, semester, and thank you for all your hard work, and hope to see many of you next year. Okay, some may be taking it at another place or the year after, but most of you are going to be in Organic 1 at least, so I'll see you then. Okay.
All right, Dr.
All
Mary.
right.
Bye, Dr.
So-
Mary.
All right, see y'all.
Bye, Dr. Mary.
Bye. Ralph, did you have a question?
Yeah, I just wanted to know like how 20.7, I'm sorry to bother you so many times, like how that 1.76 came to be, because when I did the math for it, the problem wasn't, aligning to what the answer we
Okay.
discussed.
So Kinsey has a question about
Yes, ma'am.
organic chemistry. For med school, I was told that you need organic 1 and 2, but if you are in the biomedical sciences concentration, then you just need organic 1. But for the biomedical, it's not mandatory. All right. Ralph, let me put this problem back up.
Yes, ma'am. Sorry.
No, that's okay.
Bye, Dr. Mary.
Bye. See you all Thursday. Okay. So what answer did you get for this part?
I actually corrected it. It was giving me some, hold on, excuse me. Let me work it out, Dr. Mary.
Okay.
Excuse me, give me 1 minute.
Sure.
Dr. Mary, I have a question.
Yes, Kevin.
I have a question too, but about the packet.
Okay.
I'll go get it real quick.
Okay. Go get it.
I'm getting, is the natural log of the initial, is that 4.00 times 10 to the 19?
I don't have individual answers.
Or example 20.7, Dr. Mary?
Yeah.
So the natural log initially was 4.0 times 10 to the 19.
Yeah. So are you seeing my screen?
Hey, yes, ma'am, I am.
Okay.
Hold on. I think I see my error right now. Hold
Okay.
on. I didn't put another significant figure after the 7.
No, what's
Okay.
the negative? What's the negative value? One of them should be negative. That is what makes the E go to 44 point something.
Yeah, I'm getting like 44 point. Yeah, I'm getting like 44.13 when I'm doing this.
So
Should
is
44.31.
44.13?
44.31, I'm sorry.
Yeah, that's right. That should give you the right answer.
Then take E power.
Oh, okay. Yes, ma'am.
Kevin, what's your question? While he's doing that.
Well, you're still
Okay, yes, ma'am.
Yeah, Kevin?
Yes, ma'am, I got it.
okay. So here, let's see, in the packet, and it says to write the oxidation half reactions.
Mhm.
Do we have to include the electrons if it's like MgO given to, like, okay, so the one that is I don't know how
You
to.
can, if it's on your computer, you can share your screen. You have that on your computer?
Yes, I do have it on my.
And look for share screen.
Yeah. I'm gonna look for it real quick because I had it, but
Okay.
yeah. Dr. Mary, you're still recording this.